Hello, today I'd like to explain what Riemann sums are and how they relate to integrals. They're a really nice and intuitive concept that often comes up in problem solving, so it's nice to have an explanation because I do feel like you need some background of what they are to understand what we're doing if we were to use something like Riemann sums in a problem, right? So let's get right into it. What are they used for and why are they actually just another definition of the integral we know? So let's say we were to have some function f of x, and I'm going to use this function as an example, but we should consider a more general case. So we have 1 over 4 times x squared, and we would like to figure out the area under this curve from x equals 0 up to x equals 2. So that would look like this area, and we also know that we could easily calculate that by just taking the integral, and in this case I'm going to generalize a little bit from a to b of f of x dx. So that's going to be the goal, but we are going to use this example to understand what's going on. Now let's suppose we don't actually know anything about integrals, and we would like to calculate this area under the curve anyways. Well, one way to do it would be to approximate it using squares or maybe rectangles and try and fit them under this curve. And that is exactly what a Riemann sum is. Now we are going to do it in a certain way, and there's other ways to do it, of course, but the Riemann sum is one specific way of doing it, and that's what we're going to look at. So let's get rid of this exact area over here, and now we're going to introduce some rectangles, and we're going to try and fit them under our curve. And as you can see, after, let's say, we add like 50 of these rectangles, we can see that we get pretty close to the actual area of this integral. So if I were to overlay these two, they're almost identical. Now the idea is to actually take the limit and have an infinite amount of rectangles, which would add up to the exact form of the integral. Now, for this explanation, we're just going to bring it down a little bit to make some things a little bit clearer and not make it too messy. So we would like to add all of these rectangles up, but for that we also need to know their area, of course. Now, the area of a rectangle is going to be base times height. The bases of each of these rectangles are actually just the entire interval divided by some n, where n is the number of total rectangles. One of them, in this case, is so small that you can't actually see it, but we do have n equals 10 here. Our interval is of length 2, which we can easily calculate by b minus a, and then we just divide it up into n pieces, and so we have b minus a over n for each of the lengths of the rectangles, and those lengths are all the exact same. Now for the height of these rectangles, we're going to have to use our function. And as you can see, each of the left-hand top sides of each of the rectangles is aligning perfectly with the function. Now this is by choice, and we could have also picked the middle or even the right-hand side, and depending on what you choose, you get an overestimate or a fairly good estimate for your actual integral. In the limit, each of these three approximations converges nicely to the exact integral, so it doesn't actually matter what you pick. Now to figure out the height of each of these corners, we're just going to pick n different x values and input them into our function. Now we get all of these heights, and of course still we can choose if we actually want to construct the left-hand top corner using these x values, or in the middle, or in the right-hand side of the rectangle. Now what's nice is that we can actually find a general formula for what we're calculating here. So let's say we were to write f of x sub k, and then k would be either some range from 1 to n, or from 0 to n minus 1. The most important thing here is that we just have n different k's, right? We can actually write a formula for x sub k in terms of just a and b and k. So this is what the general formula looks like. Now it's actually really intuitive. So let's say I were to start off with k equals 0. Well, then that expression just simplifies to f of a, which is of course the function at our left-hand side of the interval. Now each time I add 1 to k, so I were to go to k equals 1, k equals 2, and so on and so forth, what I'm doing basically is I'm adding 1 of the b minus a over n's, which is the length of the rectangles. So do think about that for a moment, because it's really quite nice to be able to understand that intuitively, and maybe also think about what would happen if k is equal to n. So if k is equal to n, then we of course get n over n, and we have a plus b minus a, which is of course f of b, where we have the right-hand side of our interval. Now, putting it all together, we of course still have to find the area of each of these rectangles. And we know it's base times height, so we have b minus a over n as a base, times whatever our f of a plus b minus a times k over n is. So multiplying those two together, we still have to add all of the different rectangles up for each of the values of k. So in general, we have a formula for any integral from a to b of f of x dx would be equal to the limits as n approaches infinity, of course keeping in mind that we actually need an infinite number of rectangles. And then we have the sum, summing all of these rectangles up, from k equals 1 up to n. As I said, we could change that, but I think this looks the nicest. And then of b minus a over n, which is each of the bases, times f of a plus b minus a times k over n, which is of course all of the heights. And that is the final formula for any integral written as a sum. So I really think that's quite nice, and I often use it in problem solving. So I hope this explanation was quite clear, and thank you so much for watching.